Any questions? Okay, so let's continue with from where we left last time. Last time we started to talk about one timing feature that comes inside the timer module, inside the HCS microcontrollers, which is the input capture function. And basically we said that this feature is very similar to the stopwatch operation, where you have a clock that is ticking, that is running. And in our case, it is that the 16-bit timer, free running timer that we discussed earlier. Whenever some event occurs, you can, using this timing function, you can take a copy of the free running timer in order to record the time of that event. So this function is basically a stopwatch operation. As I said, where you capture the time, you take a copy of the free running watch or the free running timer when some event occurs. And this event basically is whatever event we are monitoring on the associated pin from port T. We said that port T is used for this purpose. So we can configure the input capture to occur at the falling edge, the rising edge, or both at the falling and the rising edges. And we went into the details last time how to configure these pins to operate as input capture functions. We talked about the associated registers for this functionality, where we can choose the trigger or the event to capture the time based on it. We said that we can enable the input capture using this register, which is the TIOS register, timer input output compare register. So these bits can be used to select whether the pin from port T is basically an input capture, implements an input capture or an output compare operation. These registers, we said, are used to configure or choose the event, whether it is a rising edge, falling edge, or both. These are the interrupt flags and the interrupt enable bits for the capture and the output compare, the input capture and the output compare. So these flags are set whenever there is an input capture on a specific channel, and this can be this event can be configured to interrupt the microcontroller. These same flags are the same when the pins are configured for output compare, which we will discuss today. How to clear these flags? We said there are two methods: the conventional way, which is writing 1 to the corresponding flag in the flag register, or basically enabling the fast flag clear mode, which is in the TSCR register number 1, the timer system control register number 1. And technically what is done here, what is achieved here is basically the flag, the corresponding flag is cleared whenever you read the capture register, or in case we are talking about the input capture, or whenever you write to the capture register when you are using the output compare, the channel as an output compare. So you don't have to clear the flag, then you read or write the channel. You just simply, if you read the register, which is the capture register, which is the register that stores the captured value, in case we are talking about the input capture functionality, then this has the effect of clearing the flag instead of referring to operations, which is clearing the flag and reading the register. The same occurs when we are using the output compare functionality. Basically, writing to the capture register will have the effect of clearing the flag if this feature is enabled. So then we talked about some applications where input capture might come handy, period measurement, pulse width measurement, and all that stuff. And we said very important thing that the input capture functionality can be used simply for interrupt generation. So in case you need to monitor multiple events and you want to interrupt the microcontroller when any of these events occur, let's assume that you want to connect 8 switches to the microcontroller, and whenever any of these switches is pressed, you want to interrupt the microcontroller. So this can be achieved using port T by enabling the input capture functionality. Without this, you have only the IRQ pin to monitor external events and the XIRQ pins. So this adds to the capabilities of the microcontroller in terms of the ability to interrupt the microcontroller based on some external events. And in this case, we have 8 events that we can monitor in addition to the IRQ and the XIRQ that we already discussed in chapter 6. So then we looked at this example in which we measure the period of some periodic signal that is observed on input capture channel number 0. So basically, we said that we need to record the time of, let's say, the one rising edge and the following rising edge. So if we know the time of these 2 events, we basically take the difference, and this will be the period of that signal. Now, this example we said last time is kind of simplified scenario because the signal is known to have a period or a maximum period of 128 milliseconds. So we said this, based on this assumption, we can set the timer, which is our time base, it's our time reference, to overflow every 170 milliseconds, so that there is only one overflow in the worst case when it comes to recording the 2 rising edges. And we discussed the idea behind that. And we said that there is another approach, which is basically we set this prescaler to any value we want, and we count how many times the timer overflow, and basically the time will be the period will be the time of the second edge minus the time of the first edge plus how many times the timer overflow times the number of cycles per each overflow. Okay, and this will be is clearer in the other example, which is the pulse width measurement example, where we want to measure the width of the pulse, which is, as I said last time, could represent the duration of some event. For example, somebody is pressing a button that is connected to port pin T1, for example, and you want to record how long the user or pressed the button for 1 millisecond, 5 milliseconds, half a second, 2 seconds, and so on. So the width, the pulse width measurement is also one of the things that are implemented in different types of embedded systems. So basically, we have a pulse that we want to measure its width. So this is the pulse, and let's say it is a positive pulse, which means it is a high pulse. So in order to measure the width of the pulse, we need to record the time of this rising edge and the time of this falling edge. So basically, we need to enable the timer. We need to, which is our time base or our time reference. We need to configure this pulse is monitored on PT0. PT0, which means pin number 0 from port T, which means we have to use input capture channel number 0. So we will need to enable input capture 0 channel by channel. And initially, we want to set it such that, configure it such that it captures the time on the rising edge. Then once we receive this, we need to reconfigure it such that it captures the next falling edge. Okay, so this is what we need to do, and the flow chart of this program is on the next slide. However, we need to make sure that the captured times are correct. Let's say this is time 1 and this is time 2. And basically we said last time that our time reference for this timing functionality is timer, the free running timer, which is a 16-bit timer. And this timer runs from 0 all the way to 2 to the power 16 minus 1. And when it goes back to 0, totally we have incremented the counter 2 to the power 16 times, which is the maximum number of increments. So let's assume that this is T1. This is T1. Here we captured the time of the first rising edge. Now we don't know when the falling edge will arrive. It depends on the width of the pulse, and no information was given about this. So how can we record the time of the falling edge if we don't have any information about the pulse width, given that the timer will overflow? Basically, we need to record how many times the timer overflows. So let's say that the timer is running. We recorded T1. So here we recorded T1. Then the timer continued to run. The best case is when T2 is within the same cycle or the same overflow cycle. If it is here, then T2 minus T1 is straightforward. However, if the falling edge arrived later in time, it arrived here. This is T2. This is T2. What is the width of the pulse? It is not T2 minus T1 because T2 minus T1 is just this time. What is the time? What is the period, the width of the pulse? It is T2 minus T1, but is it this time only?
No, plus the overflow.
Plus 2 to the power 16. So if we are talking about number of increments, so the counter basically does not record time, right? It records the number of increments. And if we want to know the absolute time, we just multiply it by the cycle time, by the tick time. So here we have the time will be T2 minus T1 plus 2 to the power 16 in this case. And 2 to the power 16 is basically the time that required by the timer to go all the way back to T1. And if we take this, multiply it by the cycle time, and the cycle time, which is 1 over E period times the prescaler, if you remember, we get the period in seconds. We get the period in seconds. So the first scenario, or let's take another scenario. What if T2 is here, but it happened after the timer overflowed 3 times? Then this will be what? 2 to the power 16 times 3.
Count.
Right? So we need to keep track of how many times the timer overflow. The timer overflow. Okay? So this is in case T2 is always greater than T1. So if T2 is greater than T1, then we need to multiply by, to take the difference, then we multiply 2 to the power 16 by the number of times the timer overflow. Now let's consider this scenario. If the counter continues, it overflow 1 time, and this is T2. Now T2 is less than T1, right? But we said last time from the example previously, it's okay if we take the difference T2 minus T1, it is modular subtraction, which means we will count how many times it took us from here to here. Now, what if the pulse lasted longer such that we have another overflow? We will take this time plus 1 overflow time, right? That's why if you go to the next slide, Here we have two cases in order to do the calculation. We have two cases. Case one, when edge 2, the time of edge 2 is greater than the time of edge 1. And the second case, when edge 2 is less than edge 1. So basically the difference is you only subtract 1 in this case from the time, from the overflow count, basically because you already will have that when you subtract T2 minus T1. So this is the idea in this example. And in order to do that, we need to define certain counters, variables. We need to record the number of overflow instances. We need some place to store the difference, the edge, the time of the first edge, and the time of the second edge. Then we take the difference and store it in diff. And keep in mind again that this difference is the number of increments in the counter. To have the time in seconds, we need to multiply by the cycle time, which is 1 over E frequency multiplied by the prescaler. So in this example, the setup was done such that the prescaler is 32, which means that the cycle time for the timer is 1.3 microsecond, which means every increment for the timer is 1.3 microsecond. Why did they pick 32? No idea. They just set any value. So this is very close to 1 microsecond. So when effectively when you calculate the difference, let's say it is 10,000 cycles, this implies that it is almost 10,000 microseconds. So it is almost 1 microsecond. This 1 microsecond is basically 1 over 24 megahertz multiplied by 32, which is the prescaler. So each increment for the timer is basically 1.3 microsecond. So this is the flow chart. Here, basically, as I said, we need to configure the input capture channel on the rising edge. Then we need to wait for the flag, the channel flag, to know that there is a rising edge, to detect, to wait for the rising edge on the channel. Once that occurs, we need to clear the flag of the channel. We need to change the configuration of the, input capture channel such that it is triggered on the falling edge. It is not written here, but it has to be written here. We need to change the configuration so that it captures on the falling edge to capture the second edge. We need to pay attention here that initially we disabled all interrupt. Once we received the first edge, we enable the main timer overflow interrupt. So we enable the interrupt of the free running timer. And what is the purpose for that? Basically to detect when the timer overflow in order to increment our counter, our software counter that counts how many times the counter overflow. So here we clear the flag, we save the first captured edge, we change the configuration of the input channel, capture channel such that it is on the falling edge. We wait for the flag again to be set. Once it is set, then we have received the falling edge and the rising edge. So basically we calculate the difference of the two edges. Then we do what we had on the previous slide, whether the second edge is greater than the first edge or not. So we do the calculation. And again, the final calculation, which is the pulse, the duration will be now in number of increments, number of cycles. Just multiply with the cycle time, which is 1.33 microsecond. You will get the time, the pulse duration or width in seconds. This is the code, so you need just go over it, please. It's not that difficult. So here we wait for the first falling edge, rising edge, I'm sorry. Here we wait for the falling edge. Okay, and here, as I said, where we change the configuration such that the capture occurs on the falling edge. Initially, it is set to capture on the rising edge. So we need to change the configuration. There is an interrupt service routine for the timer overflow, and the main purpose of this interrupt service routine is just to increment this variable, which is the counter for the overflow instances. Okay. The same program in C. Here we are using C. Okay, and here we have the calculations here. This is the interrupt service routine for the timer overflow. It is interrupt number 8. So this is how we write it, as we said earlier in chapter 6. Okay. Any question? Okay. All right. The other timing functionality that comes with this timer system inside the SCS12 microcontroller is basically the output compare functionality. And I always, this is very similar. If the input capture is similar to the stopwatch operation, the output compare is basically similar to the alarm operation that we have in our watches. So the output compare basically is, this function is basically uses the free running timer such that it always compares the free running counter with some set value or with some alarm value. Once the alarm value equals the timer value, then you can configure the timer system to perform some operation on the corresponding pin from port T. So it is kind of an alarm system. It is like what you do when you set an alarm on your watch. You say, specify a value, and this value is continuously compared to the free running watch that you have in your hand. Once they are equal, the alarm, the sound will alarm. The same thing here, you have the 16-bit free running timer. You can choose or set or specify some alarm value or set value. The hardware inside the timer system will continuously compare the free running timer with this value, set value. When they are equal, you can do something on the corresponding pin from port T. And what events you can do on the pin? Basically, you can either pull the pin high, pull the pin low, or basically toggle the pin. If it is high, make it low. If it is low, make it high. So each of the output compare channels, which are basically the IC channels from port T, port pin T0, pin 1, 2, and so on. These are the same pins for the input capture. That's why we said last time, you cannot enable the input capture and the output compare functions on the same pin at the same time, because the pin is shared, the capture register is shared, which is the TC register, but now the functionality of the TC register is different. It stores the alarm value or the set value instead of being used to store the recorded or the captured time. It is the same as the input capture register. There is a hardware comparator, 16-bit, that continuously compares the timers, the timer value, and the set value that you store in the TC register. There is a pin where you can do, as we said, make it high or low or toggle. There is an interrupt request that is associated with each of these output compare functions, and such that whenever there is the timer equals the set value, you can interrupt the microcontroller, which are the same interrupt enable bits and the same interrupt flags for the input capture functionality. There are additional two features associated with this output compare. One of them is the forced compare function and the OC7 control, which we'll discuss later. So this is what I said. The operation is basically to compare the free running timer with the set value such that when they are equal, you trigger some action on the associated pin. The steps to use the output compare functionality is basically we need to configure and enable the output capture channel in order to specify the alarm value or the set value. Basically, we read the current time from the timer, we add a certain value to it in order to achieve or to calculate the alarm value. Then we store it back in the TC register. So we make a copy of the current content of the counter. We add this copy to the value that equals the desired delay. So the value that we store in the TC register is not the absolute value. It is the current time plus the time difference that we need to wait until the event occurs. When the value in the counter register equals the value in the capture register, then some event is triggered on the pin, and the microcontroller can be interrupted if you enable the interrupt. Okay, we said this, that on the pin you can pull it high or pull it down, or you can toggle it. In order to specify this, what happens on equality, when the counter equals the capture register, you need to use these two registers. You can specify whether to pull it high, pull it low, or to toggle. When the compare is successful, in other words, when the timer equals the set value, the flag, the corresponding flag of the output compare channel is set in this register, which are the same flags for the input capture, as we said, and we can enable the interrupt to be for this event to interrupt the microcontroller. Here we have the registers, which are control register number 1, control register number 2, which can be used to configure what to do with the output compare pin, whether to toggle, whether to clear, whether to set, or basically you can choose to do nothing. You don't affect the pin, but still there is comparison being done, and this comparison can be used to interrupt the microcontroller or can be pulled. And this is one way to generate time delays using hardware. Basically, you use the output compare, but you don't affect any of the pins in port T. So here the timer is disconnected from the output pin, but still you can generate an interrupt when there is equality between the timer and the alarm value. And this is useful actually because it is kind of a timer. It is kind of a timer. You are using the timer to generate delay. Here we have an example. There are many examples actually, but I will discuss this example only. I'll leave the rest for you. Generate an active high 1 kilohertz digital waveform with 30% duty cycle on port or on pin PT0. In other words, the pin number 0 from port T. In other words, we want to use output compare function number 0. Use the polling method to check the success of the output compare operation. The frequency of the e-clock is 24 megahertz. So basically what we have here, we want to generate this signal continuously on pin number 0 from port T. We can do this without using the output compare, right? We can do it using software delays, basically, such that we output logic high for 300 microseconds, then we output low for 700 microseconds. But if we do it using software, then we will keep the microcontroller busy doing that, busy executing delay subroutine. So this will consume or reserve substantial resources from the microcontroller. What is the alternative? The alternative is to use this dedicated hardware which is the timer module, in order to free the CPU from doing this. And technically, this can be done using the output compare. What will we do basically is we will initially we will take the current time. Let's say at this moment we read the current value that is inside the timer register. We add certain number of increment that is equivalent to 300 microseconds. Then we set the pin high. Now after 300 microseconds, the flag will be set. So we will read the current time, then we will add 700 microseconds to it and output 0. And we will keep doing this over and over. So basically, at the beginning, we start by reading the timer, the current time. We add certain number of increments that is equivalent to 300 microseconds. We set the pin high, then we wait for the flag to be set. Once it is set, we read the time. We add the current time from the timer. We add what is equivalent to 700 microseconds in terms of increments. Then we set the pin low. We wait for the flag to be set, and we continue to do this over and over. So basically, in order to do this example, we need to enable the free running timer. We need to specify the prescaler. We need to configure the output compare channel number 0. And we need to write the program to do what I just said. So basically what the book did, it set the prescaler to 8. Now if we set the prescaler to 8, then each increment is basically 1/24 megahertz times 8, right? So this is 1/3 microsecond, which is 0.33 microsecond. So every tick, every increment in the free running timer is 0.33 microsecond, is 0.33 microsecond. So what is the number of increments in order to have 300 microseconds? We need 3,000 clocks. 3,000 clocks times 0.33 will give us the number of increments that we need to add, which is 0.33, which is almost 900 increments. And the same thing for the 0.7 times 3,000, we will have 2100. So again, to have 1 millisecond period, we need to count for 3,000 clock cycles. It is a 3,000 times 0.33, which is 1 millisecond, which is the period of the 1 kilohertz. 1 kilohertz. So for 0.3 or 30% duty cycle, 30% of the 1 millisecond is basically the 300 microsecond, which is basically 900, because 3,000 cycles equivalent to 1 millisecond. 0.3 or 30% of the 300 of the 3,000 is basically 900 increments. The same thing for the 70% part of the signal. So we need to do these settings, and at the same time, we want to do what I just said. We need to capture, record, take a copy of the time, add 900 cycles to the capture to that value, store it in the capture register, and output high. Then wait for the flag to be set. Once it is set, read the current time from the timer, add 2100, output logic low, then wait for the flag to be set, and so on. Okay. So if we look here, we are adding different values. We are adding different values to the current time from the timer, depending whether we are outputting 1 or we are outputting 0. So we need to keep, in our program, we need to keep a track, whether we have to add 900 now to the current time or to add 2100 to the current time. To do that, we need like a flag or a variable that keeps track whether we should add 900 or 2100. So this is the flow chart. We need to set output to enable output compare output compare 0. This should be 0, or that should be 0. This should be 5, because everything over there is about 5. So this is on channel 5, but it makes no difference on any channel, because everything here is on about is or considers channel 5. So on channel 5, we need to enable the output compare function. We need to clear the OC of output, the flag, the corresponding flag. Then initially what he did here is basically he wants to toggle the output pin. Instead of outputting 1, then outputting 0, he wants to toggle. So he wanted to have some initial state for the pin. So he started output compare operation for 10 cycles only, and it set the pin to high. So the next time he will start adding 900 and toggling the pin. Then add 2100 and toggle the pin. So, so the program will not output 0, then output 1, output 0, output 1, and so on. It will just toggle the pin. So to toggle, for the first time, you need some initial state for the pin, and this is achieved by outputting logic 1, outputting logic high on pin number 5 for 10 cycles only, using the output compare. And how to do that? We read the timer, we add 10, we store to the capture register, and we wait for the flag. Once the flag is set, then 10 cycles have elapsed. 10 cycles times 0.3 microsecond implies 3 microsecond. This is just only to have an initial value for the pin, because we want to toggle it later. So this is just for initialization. Next, we set the pin to toggle. Then we have this variable high or low. It is a variable in memory which keeps a track whether we are in the high portion of the signal or in the low portion of the signal, in order to know whether to add 900 to the time or 2100 to the time. So initially we set this to 0 to indicate that we are in the high. I guess it is 0 with low count. No, 0 implies it is in the low count. So we should add 2100. Start a new output compare operation with delay equals to HI count. So we have two counts, either 700, 900, or 2100. They are called high count and low count. High count and low count. Now, this operation is not implemented using polling. It is implemented using interrupts in order to free the microcontroller, because we want the hardware to continuously output that signal without any resources being used from the CPU, except at the beginning only to configure the timer module. So whenever the flag is set, this implies the compare is successful, the interrupt will occur. So at the beginning, we'll check this variable, whether we are in the low or in the high portion of the signal, in order to decide whether to add the low value or the high value to the timer, to the time that we have from the timer. In other words, whether to add 2100 or 900 to the timer. Then we change the status of the system. So if we were in the low portion, next time when the interrupt occurs, we are in the high portion. So we go here. Same here, we change back the status of the program to the low whenever we are in the high portion. So this is the program in assembly. Let's look at the C version of it. In the C version, everything here is all about configuration. Enable the timer. We need to enable the timer with fast timer clear, fast flag clear. Disable the interrupt of the timer system. and set the prescaler to 8. Enable output compare 5, and this is done by writing to the TIOS register this mask, which is OC5. OC5, this implies that bit number 5 will be set, while the remaining bits will be 0 to enable output compare on channel 5. Then we set OC5 to pull high, which is for the initialization only, to have some initial value for the pen. We clear all the flags. Here, how to use the capture function. We read the register, the counter register, which is the free running timer register. We add 10 cycles to it, which is this very short time to initialize the pen. Then we wait for the flag to be set. As long as it is not set, then there is no successful comparison. So we need to wait. Otherwise, we move and we set the pin to toggle. Then we add the high count because we started from the high. So we want to count. So the high count, if you look here, it is defined as a constant with 900. So we add 900 to TC5. Now at this moment, TC5 is basically almost the same time as the timer plus 10. So we add the high count to TC5, which is effectively the TCNT plus 10. Or we can do the same, actually. We write TC5 equals TCNT, which is the current time after executing these instructions, plus this constant. We change the state of the program to 0 to indicate that next time when the interrupt occurs, we should add 2100 to the program. Then we enable the interrupt locally for channel 5, so that when there is a successful comparison, we change the status of the pin and we change the time to be added to the TC5 register. I'm sorry, to the timer, so that we change the capture register. All right. Of course, here we have enabled the global interrupt globally, and here we have an endless loop. Nothing will happen here, assuming that here we don't have any other tasks to be performed. But usually there is something else to be done, and that will be part of the endless loop, in the main loop in the program. So after this point, the CPU has nothing to do with the generation of that signal on pin number 5 from port T. It is already, it will be done completely by the hardware. We just configured it, and it will be generated automatically. Okay. So this is the interrupt service routine, and here the example uses the large memory model, and we talked about this in chapter 6. When writing C programs, we said we need to specify the memory model. For small models, we said there is a different way to define the interrupt service routine when it comes to large memory or segmented models. There are other examples here how to write a time delay that is multiple of 1 millisecond using the output compare. So it is just, you need to do some calculations, then you just configure the output compare functionality. More examples are in the textbook. We have 8.6, 8.7, so look at them, some applications for the output compare. Okay. Now, some features that come with the output compare functionality is controlling multiple output compares. Technically, this feature allows the output compare channel number 7 to control the remaining channels, such that when there is a successful comparison on output compare channel number 7, you can configure the system such that all other output compare channels are affected in a certain way. So in other words, output compare channel controls the remaining output compare channels in a certain way, such that it forces the output to be, let's say, high, low, and so on. So basically, you can use this feature to in some applications to control all the output compare channels. And to do that, there are special registers related to that. We have OC7 mode register, which specifies which output compare channels are controlled by OC7. Channel 0, channel 1, channel 2, all of them, some of them, and so on. And we have another register, which is the data register, which basically specifies what happens to these output compare channels when there is a successful comparison on output compare channel number 7. And this basically, if this feature is enabled for one or more of the output compare channels, it overrides a successful comparison on these channels. So if it happens that you enable, let's say, output compare function number 0, channel number 0, and you allow the channels number 7 to control channel 0, and it happens that there is successful comparison for channel 0 and channel 7, what will happen to channel 0? It will the successful completion on channel 7 will override the successful compare on channel 0. In other words, the value that you specify in the data register here of OC7D will appear on that pin, not the value that you specified in for channel number 0. So here we have the two registers where you specify which channels are affected by OC7 and what happens to each of these channels if you enable this feature, whether you want to output 0 or you want to output 1. So here you store the value to appear on this pin, for example, when you enable channel 7 to control this, to control channel 0. So if you write 1 here, then you say that when there is a successful comparison on channel 7, you want this value, the value that is in this bit, to appear on channel number 0. So this is very simple idea. So you can control up to all these channels. This is an example. What value should be written to this register and this register if you want, if one wants pin PT2, PT3, PT4 to assume the values 101 respectively when OC7 compare succeeds. So we want to control channels number 2, 3, and 4. So we need to write here 1, 1, 1, because we want this to affect these channels, and the value to be output when there is a successful comparison, it is 101. So we need to write here 101. So when there is a successful comparison on channel 7, these pins, the pins associated with output compare 2 through 4, will have these values on the pins, output on the pins. So this is two simple instructions to do that. Okay. So if we look here, the value to be output is 1, 0, 0, 0, 0, and this has to be, of course, 1 because you want to affect channel 7, and this is 1. I'm sorry. And here we have 0, 0, which is the reset value, and this is 0, 0, 0. So the value to be stored in this register is 1, 4, and the value to be stored here is 1, C, which are the values that we have here. Another feature that is associated with the output compare is the forced output compare, which is basically, I always say it is like an emergency feature. For example, if you configured one of these output compare channels to do something after some time, so you configure the channel, you read timer the timer time, you add the delay, then you store in the capture register. However, while the program is running, your program discovered that it has to force the channel, to perform the required operation now. It doesn't have to wait until there is a match between the capture register and the timer register. In this case, you want to force the channel to perform the required operation now, not by the time when there is a successful comparison. So this is called a forced, output compare, in which we force the channel, the output compare channel, to perform the configured operation before the time has arrived. And to do so, basically, there is a special register, which is the channel force register, where we have 8 bits. And here, if we write 1, for example, to this bit, then we are telling the timer system to output the configured value on channel number 7 now, before there is a successful comparison between TC7 and the timer register. Okay, so first,
What does it exactly compare here?
in this register,
Yes.
basically we write the channel that we want it, or we want to force it to behave or to output the configured value. We just write 1 here. So for example, if as I said, if you are using channel number 7 such that when there is a match between TC7 and the timer, you want to output 1 on pin PT7. Okay, so you configured the system to operate like this. When there is a match between TC7 and the timer register, we want to output logic 1 on channel number 7, on pin number 7 from port A. However, you discovered that there is an emergency and you want to force the pin number 7 from port T to high now, and you can't wait until there is a match between TC7 and the timer register. So if you go to this register, the C force register, you write 1 here. This will force channel output compare channel number 7 to output the configured value, which is in our example is 1. So this is important because your system that you built might be controlling some device, and this device has to be, let's say, enabled like an alarm system, or let's say a water pump or whatever, and is configured to using the output compare system. Using the output compare system, you want to turn on the pump at certain time. But however, you discovered while the program is running that there is an emergency and you want to turn on the pump now. So basically, you go to this register, you write 1 here, and this will force the output compare channel to output 1, which is the configured value. Now, without waiting for the match between the TC register and the timer. That's why it is called forced. You force the channel, you push the channel to trigger the pin now, to change the value of the pin now before the comparison is successful. Okay, so this is an example about it. Very straightforward. What will happen if some channels are, for example, what does it say? Okay, so this example is straightforward, just to figure out the values to be stored in order to use the forced feature. The forced feature, what values, no, it is not this example. If the contents of the TC control 1 register and control registers are this and this. And these registers, if you remember, these registers determine what happens to the pin when there is a successful comparison for the output compare channels. So every 2 bits in these 2 registers specify what happens to the pin, whether it goes high, whether it goes low, whether it toggles, whether nothing happens to the pin. Also, it says that the contents of the flag register are zeros, which implies that no compares were successful so far. What would occur if pin PT7 to pins on pins PT7 to PT0 on the next clock cycle if the value 7F is written to the C force register? So in other words, we write 7F to the C force register. If we go back, 7F, it implies we write 1, 1, 1, 1, 1, 1, 1. What does this imply? If we write this value to this register, 0, this implies that we want to force channels 0 through 6 to output the configured value. And how to know the configured value? Basically, by going to the control register number 1 and control register number 2. And these are given here. Control register number 1, control register number 2, bit position number 7 and 6, value 1, 1, based on the values that are stored here. Control 1, it contains D6, 6E. So D6, D is what? 1, 1, 0, 0, 1. 6 is 0, 1, 1, 0. So these bits control channel number 7. The values are 1, 1. So this implies if you go back to the register, the output compare action will be to push or to pull the pin high. Pins 4 and 5 are 0, 1. So 0, 1, if you go to the description of the control register number 1 and 2, this will toggle pin number 6, PT6, and so on. So here we have the bits that specify what happens on each of these output compare channels. And technically, because we are writing to this register, this value, then we will force these pins to have the configured value, which is listed here now, not by the time when there is a successful comparison for this channel. Or even you might not be using the output compare function for these pins, but you want to use one output compare function, which is 7, to control 8 pins at the same time. To control 8 pins at the same time, but differently. Some of these pins may output 1, may output 0, may toggle depending on your configuration. So this is about the output compare. So if we go back to the block diagram of this timer system, we covered the free running timer. We covered the free running timer, the 16-bit timer, and we said it is the base or the time reference for other timing operations in this module, which are the input capture and the output compare. And in this module, we have 8 input capture or 8 output compare channels, which are associated with Porty. What is left in this module is the 16-bit pulse accumulator, which is usually covered, I cover in the second part of this chapter. But as I said last time, I will drop this part for this semester, and I will consider this the last lecture for the material to be considered in this course. This will give you more time to work on the term paper that is due next Wednesday, right? It's due next Wednesday. So next Wednesday, I will add a link on e-learning for you to upload your report. Please make sure to upload your paper through that link. Please try to put significant effort when you prepare the survey paper or the critique paper, because as I said, this is an exercise for you. Try to exercise now. I know it's difficult always at the beginning to learn something new, to do something new, but it is an exercise. At the end of the day, you will you will do this. You will have to write a paper. We will write your thesis and so on. So once I receive your reports, I will try to go through them, and I will post, and I will send you a notification on the system and an email regarding the presentations. So the presentations will be the week after next Wednesday. What is the number of students? We have what? We are 6, right? We are 6 students. Fatma is no longer interested in the course.